Welcome, everyone. Should I go stand here? I didn't ask before. Well, I'll go here. So, hello, everyone. Welcome to, this first day of ComCon and this room. I'll be helping out and trying to keep things going smoothly. Our first speaker is Begen, currently computer science professor at Begen University, and more importantly, a technical consultant for Comcast, and is going to talk about the topic that I really like very much, which is media over QUIC, a new standard, a new idea of low latency broadcasts that are synchronized and will help with sports and all things broadcasting. So, thank you, Ali, and take it away.
Thank you. Thank you very much for the introduction. So, all right. So I gave a shorter version of this talk last week in Berlin, and there were a couple of references, including this title and and a couple of other slides to the movie Interstellar. Unfortunately, many people didn't get those points. I hope this crowd will be a bit better. So media over QUIC. This is something people have been planning or thinking about for a long time, and finally it was put into action last year in the IETF. And then I'm going to talk about current developments and what we are doing with it, and what we might be using it for in the future. But I thought the keynote would be a bit boring, but it wasn't. So I thought, I will start with a fun video about British people. But let's see. Just to wake you up first in the morning. There's supposed to be audio, but
We are, however, operating a replacement bus service.
Something one of my friends sent me yesterday, so I thought it was funny. So each time I visit the UK, I really learn new things. It's not, obviously English is not my native language, but again, the pronunciation, the spelling, and then the meaning of the words are quite different. So it's always fun to visit the UK. So just, this is my first time at ComCon. I've been a speaker at DMAX, Smile High Video, and a bunch of other video events, primarily in the US, and then also a Media Web Symposium in Berlin, which takes place in Berlin every year. Hosted by Fraunhofer, but this is my first time in ComCon. So just to give you a bit introduction. So I'm originally from Turkey. Now the official name is Turkey, actually. I was born, raised, and currently living in Konya. That's the capital of Selçuks. Before the Ottoman Empire, Selçuks were in the region, and that's the capital. So the history of the city goes about 5,000 years into the past. And that's also the city of Rumi. If you have seen whirling dervishes and things like that, that's where my hometown is. And then I went to college, my electrical engineering degree. I got it from Bilkent University, the first private university in Turkey. And then I moved to the US to do my PhD at Georgia Tech in electrical and computer engineering, along with a computer science degree. And that's when I finished in 2006. In the meantime, for a year, I did an internship in San Diego, beautiful town in Southern California, with Qualcomm. And then once I graduated, I started working for Cisco in the research and advanced development group. So I was in Bay Area for a couple of years, and then I moved to London, Ontario, which is close to Toronto. And, I worked about 9 years at Cisco. Last 3 years, I was back in Turkey because I wanted to get married, and then it didn't really work out very well when I was in North America. So I came back, I got married, I kept working for Cisco for about 3 more years. And then, as you can see, that was a big, fat wedding, 2,200 people. I barely knew 200 people probably in that wedding. And then, I had to leave Cisco for a variety of reasons, but I said, I should continue in academia, and I joined another private university in Istanbul, Özyeğin University. And the owner of that university, or the founder of that university, happens to be the richest guy in our country. So that turned out to be a good deal. And and then, I've been there since day one for Dash, MPEG Dash development. As I said, this is my first time in ComCon. I'm actually a streaming guy. I did a lot of RTC stuff in my PhD thesis dissertation, but since then I've been working on streaming media. Although last 5-6 years has been the focus has been on low latency. Many people would know me as a streaming guy. And I was one of the co-chairs for MPEG Dash working group in MPEG, and we got a technical Emmy award last year about the standard. And then today I'm really happy where Dash is. Obviously, there's an elephant in the room called HLS, but if you want my opinion on that subject, I'll be happy to speak to you in the break. So today's talk is about media over QUIC. So it's like intersection between streaming and media, real-time communications. So all kinds of applications you can think of, obviously WebEx, Zoom meetings type, team meetings like that, online doctors, online health, metaverse, online teaching, distance teaching, learning, all that stuff, right? So this is where streaming is going to have more interactivity features, but then also the interactive applications will hopefully be able to scale to much larger audience, right? So let's start with some basics. I suppose many of you know about the QUIC protocol. This was developed initially by Google several years ago, and then it was brought to the IETF, Internet Engineering Task Force, which I've been participating in since 2006. And that's really a protocol meant to replace TCP eventually, right? It is running over UDP. It's a user space protocol built on top of UDP, but it gives you the reliability and then other features that TCP has. And on top of that, it gives you a lot more flexibility in terms of settings, configurations, and things like that. So, you can today use, obviously, we still use TCP, and then on top of that, TLS, Transport Layer Security, and then HTTP2. Many browsers, websites still support those. But if you use QUIC with HTTP3, which I'm going to talk about, you will get a bunch of new features like, connection establishment latency will be really, small. It could be 0 RTT or 1 RTT. And then you can pick your own congestion control, so you're not really stuck with whatever the operating system gives you. So you can change this also in the application space. That also gives you improved retransmission efficiency, right? And then, you can pick your own retransmission rules, which is obviously helpful for real-time communications. One of the most important features is the avoidance of head-of-line blocking, which is a big deal when you are using TCP. And then the connection migration, if you are in this Wi-Fi, you move to LTE or 5G and then come back to Wi-Fi again. All this is rather seamless if you use QUIC. QUIC gives you reliable, so it's built on UDP, but it gives you reliability still by doing retransmissions in the user space. And then it also gives you prioritized delivery, because a single QUIC connection can have multiple streams within the same connection, and then each of these streams can have a separate priority. And by adjusting the priority appropriately, you can give more bandwidth to a particular stream over the other. So that will give you some sort of, maybe deadline-aware type of transmission. And then this is also, this has, again, each connection has a congestion control and flow control. So all the nice features that we need from TCP. And then the prioritization is adjusted by the sender side, on the server side, I mean. So separate logical streams, multiple streams within a single QUIC connection. And then within each stream, there's an in-order delivery. So stream 1, if you put a bunch of packets in stream 1, they are supposed to be delivered in order and then in a reliable manner. But they are independent of the delivery of the packets in stream 2. This gives you a lot of flexibility when it comes to media transmission protocols. And then you can also have partial reliability, which is an extension to the initial QUIC. So you can also have unreliable QUIC streams if you want to. So you don't care about retransmission much, maybe about those data packets, and then you can just skip them, right? One of the things that people need to understand is QUIC is a very much encrypted protocol, so it doesn't really expose too much information in the headers, unlike TCP does. So whenever you look at, if you're a network operator as coming from a Cisco background, when you look into the packets, you will see a bunch of headers and then the payload. But then pretty much everything that is relevant to us in the network space is going to be encrypted. So when we look at the quick connection and quick packets, it will be a one single encrypted connection. There could be multiple streams, but we won't be able to identify them within the network. So even though you are prioritizing your stuff at the center, the network will not actually know that you are prioritizing this stream or these packets over these packets. You need to expose something else into the network or into the middle boxes so that the system components can make use of that. And that's one of the primary discussions we are having in Media over Quick. So just a quick summary. HTTP2, that was based on Google's speed algorithm. That's still based on TCP, as you know. That's RFC 7540. It took how many revisions? Probably more than 17 versions or something to be finalized in the IETF, right? And then, they started with the quick in mind in HTTP2, but they said, okay, let's separate these things from the HTTP syntax and then make it a separate protocol, and then it will have its own HTTP protocol, which is HTTP3. So Quick has Quick had 34 revisions, as you can see. The Google Quick versus regular IETF Quick actually kind of diverged at some point, but then eventually all the current existing implementations are supposed to be IETF compatible. So if you take Cloudflare's or Google's or somebody else's Quick implementation, they should be compatible with each other. And then H3 has also become a standard last year. So RFC 9114, and that's most of the new browsers obviously support if you go to certain websites. So this is a nice animation showing how Quick actually avoids head-of-line blocking. On the left-hand side, even if you, for example, you are making a request to a HTTP server, you are getting two objects in the same TCP connection, yellow and green, and then even if you lose a packet from the yellow one, the whole transmission stops. Well, the transmission doesn't stop, but the application delivery, the data that you receive to the application will not be delivered. So that's what we call as head-of-line blocking. In the Quick case, if you lose a yellow packet, only the yellow data stream will be affected. The green will still be delivered to the application. So imagine that maybe the green ones are my iframe data packets, and then the yellow ones are pframe packets. So, I will be losing the pframe packets, but not necessarily stopping the iframe data transmission. Another slide, I'll just keep it as a reference. This is from Ably that shows the difference between different HTTP versions and the features that we have in each protocol layer. I keep mentioning this HTTP3 because that's where we are going to use Quick and the Media over Quick in this talk. So we have been doing a lot of research. I have a bunch of grad students working with me. Not for me, working with me. There's a difference there. So we've been doing a lot of testing, and then a lot of other research groups around the world, they have been also doing similar tests. And then pretty much everybody agrees that Quick really performs better than TCP, but especially in congested environments. If everything is beautiful and working nice and well, you are not going to really see much difference, because at the end of the day, the congestion control and rate control algorithms are going to be more or less the same. But the conclusion is that we still need an application layer, a custom application layer protocol, if it is an HLS- type of application or another real-time media application, so that we can actually reap all the benefits Quick can provide. If we are not aware of what the features Quick has or can offer to you, you are not going to make any use of that. And if you are running on HTTP3 browser in a JavaScript application, well, it is not going to give you any advantages. That's unfortunately the case. So most of the streaming methods that we have today, including Dash.js, HLS.js, and all kinds of other JavaScript-based, MSC-based applications, or a lot of WebRTC applications, they don't necessarily understand what type of transport they are running. And then even if they know TCP versus UDP, now Quick is in place, you still need to understand what those features you can benefit from, and you need to make use of them. Unless you do that, you're not going to get really any better results. Okay, that's weird. And then there are a couple of sample readings here, if you want to look at this subject in more detail. So today, this is an RFC we published, I think, last year, 9317 in the Media Operations Working Group in the ITF. There's all this latency landscape, right? High latency applications, typical latency, low latency, ultra low latency, and then near real-time latency applications. I don't really necessarily like this categorization, but that's, that was the best we were able to come up with. So 100 milliseconds barrier, 1 second, 10 seconds, and then 45 seconds. So you can use Dash HLS with different segment sizes and with different, transmission schemes to get anywhere between, 5 seconds to 50 seconds or so. That's typically the delays latencies we get today. And the regular over the cable or satellite or IPTV broadcast is around 6 to 8 seconds or so. But then any other interactive application, depending on the level of the interactivity, we are going to require less latency, right? And today, this Media over Quake is going to focus on this latest, the most right-hand, latency values. So it's, multiples of hundreds of milliseconds. So this Media over Quake working group was established last year in the ITF after a long mailing list debate. And this is meant to offer a new transport protocol approach for applications running on top of Quake, right? And then one-to-one, one-to-many, or many-to-one type of application. So it could be like a broadcast application. It could be like a one-to-one video telephony or video conferencing application, or it could be many-to-one. So it's multi-point conferencing applications. Now, on one hand, we have Dash or HLS type applications, and they are tremendously successful, right? Today we live stream all Formula One, Olympics, championship final games, all those games in live, and then with not really much latency, and then to millions of people, World Cup, for example, right? On the other hand, we have all these nice WebRTC applications or real-time RTC applications, right? Real-time communication applications. And what we want to do is that we want to improve the interactivity of Dash HLS type of applications, and we want to improve the scalability of these RTC applications. That's where MOQ comes into place. That's the goal for this working group. So the way we envision that it's going to work is that there can be multiple senders, right? One or more senders. There can be one or more receivers. And then the replication, the network efficiency is going to come through the relay points in between, just like your CDN nodes, right? So in HTTP streaming, we use all these cheap CDNs, that will cost you just a few cents per gigabyte to video delivery. And just like that, we will have MOQ relay points, MOQ CDNs to offer you these services, hopefully, probably not that cheap, but hopefully really at a reduced price. Because we cannot really scale this without the relay points, and relays are really first-class citizens in this MOQ protocol. And by the way, this can run in web transport directly on HTTP3 environments or raw Quake. If you are not using an HTTP environment, you can use raw Quake sockets for that purpose. So what we did, the first implementation from, for MOQ was from Luke Curley from Twitch. He's no longer at Twitch, but I mean, he has this implementation called Warp, and he's still actively maintaining it. And then we took that code, it's available on GitHub, and then we tried to understand, what was missing. And then we tried to complete those missing blocks and then, improve as much as possible. So these are the things that we've focused initially. Some back and forward informational messages, control messages between the server and client, some clock synchronization stuff, and then bandwidth measurements, which is really important because of rate adaptation purposes. The initial code didn't have any of those. And then we need some enhanced logging so that we can actually identify what we were doing, whether we were doing it any better or not. I really apologize for this really weird color. I don't know. It looks red on my screen, but anyway. So the client side, the server side is relatively simple for Warp. And what it does is that, it maintains a bunch of video files they're all pre-recorded, but they're being read and then streamed out of the server just like a live stream. And on the client side, you go to a web page. This is running around web transport. You create your quick connection, and then you receive a couple of control messages and so on, and wait for a new incoming stream. Remember, this is not like Dash or HLS where the content is actually pulled by you. This is rather a push protocol where the content is pushed to you from the server to you once you load up the page. You get the initialization segment, you know how to decode the video and all that, and then you start piping your incoming data into your video decoding pipeline, and then as you decode them, you display them, right? And then in between, we do bandwidth measurements, and based on that, we perform rate adaptation. Remember, one of the most important features for Dash or HLS is rate adaptation. So your bandwidth conditions might change, right? Your Wi-Fi conditions might change, so you need to adjust so that the flow doesn't stop, right? So you can go to this URL, that URL, or scan this QR code to see the demo, and you're gonna see, it looks really ugly there, but hopefully you will see some really nice, statistics about the application. So the code is available there as well. We are continuously making improvements, so as we make more progress, you will see the new versions on that page. So media over Quake, that's streaming.university. And below you see some plots, which I'm going to show next. So one of the things Luke was advocating in its own implementation was, the server knows the best about the network bandwidth. So it is directly getting the network bandwidth, available bandwidth information from the quick congestion layer, congestion algorithm, and then adjusting the bandwidth, the rate of transmission to that value. And for those who know me, I'm all for client-based rate adaptation. I've been saying that for years, and then I'm still arguing for that. And then we said, okay, look, the guy's name is Luke as well, but hey, Luke. Your results are good, but I think we can improve them. So this is what's happening. Just to give you an idea over here. So the blue curve is the bandwidth limitation from different profiles from Dash Industry Forum. And that's what we are applying to the client or using the TC tool. And, those details were the more detailed results were just presented in Vancouver a couple of weeks ago in the MEMSIS conference. And here is the paper reference. So the black pluses are the values estimated by on the sender side by the congestion layer algorithm, congestion rate algorithm. So here, for example, the server thinks it can send at 6 megabits per second. Well, actually, the network throughput is about 3 megabits per second. So it's usually overestimating or over predicting what it can send. On the other hand, we have two algorithms that we were proposing and studying. The red ones and the green ones, as you can see, they're a bit closer to the blue curve, which gives you a better prediction value. With better prediction value, you better, rate it up better. So those algorithms are using every frame versus only iframes. That's the difference. Smoothed weighted moving average versus only iframe average. And details are on that page again. The iframe ones, the green ones, are a bit easier to compute, but eventually, they are quite similar in terms of performance. Now, one of the things, okay, here's another video. I don't think there's an audio in it, so let's see. So this is what we were, working on late last year, and as we developed our code, obviously we were always, constantly in touch with Luke and other people who were really, desperately working on MOQ implementations, and we did a couple of good things. But then when we gave our code to them, they tested it, and then this is what happened. So, and then we came back. Obviously, okay, let's fall back and see what we did wrong, right? Not in terms of bandwidth prediction and so on, but in terms of the MOQ implementation. And this was not really our only fault. I mean, this was pretty much everybody was missing, I guess. So I'm going to talk about really something simple, but it makes such a huge difference. That's why I want to illustrate it. So when you are encoding data, you have a camera, you are encoding in real time, you are producing iframes, p frames, b frames, whatever. It doesn't really matter how what's your GOP structure and so on. Obviously it matters, but just as an example, you produce an iframe, and then p frame, and then some b frames, and then another p frame, and then b frames, and so on, right? So as these are being buffered on the server side so that they can be transmitted. So this is your first link, right? You are going to upstream, or you are going to send them from your computer, your camera, whatever, right? So there will be some sort of waiting, because you might be encoding at 10 megabits per second, but maybe your link is not really, or your transmission layer is not able to send at 10 megabits per second. So there will be some, queuing. If you have enough bandwidth, obviously that queuing is not going to be really much, right? You will get your really huge iframe, and then you will send it out. You will get your p frame, you will send it out. So when things are running normally, there's not really a problem. QUIC or TCP, whether you use a single stream versus multiple streams, it doesn't really matter. So first encode, first send just works fine, right? But things really get complicated when there is some sort of limitation on this link. So you are again encoding at 10 megabits per second, but let's say this link is running at 2 megabits per second right now. So your frames are going to accumulate, right? Your queue is going to build up. Let's say, because of large memory, you're not going to run out of memory, but it's going to introduce latency. That's the very basic known problem in real-time applications, right? Important stuff gets delayed when things go bad. So we need to fix this. And that's when, if you go to that demo page, you will see that most of the time your latency is going to be a couple of 100 milliseconds. Perfect. But when you get a bad Wi-Fi or something like that, it's going to increase right away, and then it's going to be really difficult to bring it down again. So my first reference to the Interstellar movie, hopefully this crowd is going to get it. So Newton's third law. The only way to move forward is to leave something behind. So what does this tell us? Well, we can use, if we are using MOQ, we can use multiple streams. And if we don't enough bandwidth on the link, we can start dropping unimportant stuff. In this case, starting with p frames and then p frames, and hopefully none of the iframes. Very simple idea. People have known this before probably I was born and so on. But this is something MOQ, media over QUIC, gives us with the support of multiple streams. So I have multiple streams in a single QUIC connection running the same congestion control algorithm, common congestion control algorithm, but then I can prioritize my frames accordingly, okay? So this is how it's going to look like. So your iframe arrives, it is served because it's in a separate queue, right? And then your p frame arrives, it is sent, and then your b frame, p frame, and so on. But you are holding on to your b frame because there are some p frames to be sent to the link, especially if there is congestion, bandwidth is limited, so I'm using that capacity to send the p frames, right? And then eventually the b frames are going to be transmitted if there is any availability. And, yes, maybe these frames are going to be delayed more than others, but you care less about these frames being on time compared to p frames or I frames. That's the idea. And MOQ gives us this capability very easily and naturally. So let's look at the latency when the link bandwidth equals to encoding bitrate. So we have a bandwidth exactly at the encoding bitrate. So things are just fitting into the pipe. By using that approach, we make sure that our iframe latency is in the order of a couple of hundreds of milliseconds, okay? P frames are going to be a bit higher sometimes, depending on, obviously, this is not exactly pure CBR encoding, so there is some DBRs in this codec. So sometimes when the iframe size increases, the subsequent P frames are going to be delayed a bit more. But look at the B frames. At some point, they go out of control. I'm running an RTC application, and my latency is around 10 seconds. Well, Obviously, this is not really as good as I would like to be, but again, if these frames are that much delayed, I'm just gonna skip them, discard them. I'm not gonna even transmit them. That's what we are doing right now. So that's what we are trying to implement at this point. Latency-aware packet discarding. So if I get rid of these packets from the system, hopefully, it will not really get this bad, but maybe, I will be still able to maintain some of the, latency under control. So, we have a very basic, simple metric, on-time display ratio. So if you have an iframe, you receive it on time, you decode it, you get 100%. If you get a P frame, you decode it, you get another frame successfully decoded. But let's say a P frame doesn't arrive on time for its own display, by its own display presentation timestamp. You skip it, so that's an unsuccessful frame, and then the subsequent B frames are going to be affected as well. So this is an interesting plot. So again, my video is at encoded 2.7 megabits per second in a BBR fashion, and now first encode, first send. You see, I'm not going to get any latency less than a couple of hundred milliseconds, but even if I have a latency budget about 1.5 seconds, right? My on-time display ratio is going to be about 20%. That means only 20% of the frames are displayed on time. It's actually is miserable. But if I use the same bandwidth with prioritization based on the frame type, I will increase my OTDR performance multiple times. So at 1.5 seconds of latency boundary, I will get 50% OTDR performance. I'm not doing anything else. I'm just separating the frames into the separate queues, and then I'm applying prioritization. If I increase my bandwidth a bit, obviously this will help, and then it will improve my OTDR performance. But then with the frame type, it will improve even further. If I increase my bandwidth to 3 megabits per second, yes, it will help with the OTDR performance, even if I don't use any prioritization. But with the prioritization, it will be even better. Now, here is an interesting data point. At 1.5 seconds, these are more or less the same. That means what? Any idea?
That for the high latency things, there's no point.
Right. So after this point, prioritization doesn't really help you. But if you have a less latency budget than 1.5 seconds, prioritization is going to give you better decoding performance. Right? And that's logical, right? That's expected. So if you look at the amount of data waiting to be sent on the server buffer, in the send transmission buffer, right? So this is a 25 frame per second video, 2-second gap, so there's one iframe every 50 frames. And this is a 100 second result, and these are my iframes, okay? So in terms of megabytes, obviously it's very less, because as the iframes are generated, they are sent right away, so there's really not much waiting happening on the sender side. The P frames are waiting a bit more. Well, not just longer, but also the amount of data is longer. Considering that the P frames are smaller in size, that means a lot more P frames are waiting in the transmission buffer. But look at the B frames. A lot of B frames are just waiting on the server side to be sent. And then obviously, if we are latency-aware transmission, you are going to cut off at some point, and then you are going to skip the rest, and you are just going to discard them, because those late packets will never be useful. Okay? So what we are doing now? Well, we have a number of AWS instances in different geographies, because we want to test with different latency values. When you test between Istanbul and Frankfurt, that's really nice. But when you test with Istanbul versus Tokyo, that's not really as nice, right? So we are trying to understand what's going to happen in those different circumstances. The BBR support, Google's congestion control, not just for Quake, but also for TCP. At this point, we have a Quick Go, but we would like to replace it with another Quick layer that supports the BBR. Quiche or Quinn will be probably our choice. We are looking in the web codecs. At the moment, we are all using CMAF package data, so there is some overhead. Web codecs API for low-level frame access, I think it's going to be useful, for further reducing the latency. And then we are looking into different stream prioritization techniques. That's important. Right now, we are just doing very simple thing, right? Frame type. But then, it's going to be like when you are in a relay, when you are running multiple senders and clients, the content itself, the number of clients watching that stream, all that stuff is going to be important. So we need to understand the prioritization a bit better. So there is one implementation from Meta based on the web codecs. That's interesting. I strongly recommend you to have a look at that one as well. There is one Cisco implementation as well. Probably others are going to come up soon. And obviously, we want to compare them as they become available. So this final slide, this is something Dan specifically asked me to actually include in this talk. So this is where we are. Well, this is not where we are now. This is where we were like about 10 years ago. This all media were quick. Not necessarily quick, but all this, unequal error protection or, prior to base retransmission, all those ideas have been floating around for a long time, right? This is now where we are writing the standard. Hopefully, the first working group adoption is going to take place in a few weeks. And then there's an ITF meeting next month in San Francisco. If you're interested, then please join that. But then I think this is when it's going to be deployed, if it's going to be deployed. So I give about 50-50 chance to MOQ. There is a huge WebRTC deployment out there. Whether it's going to replace WebRTC or not, that's TBD. Same thing goes for Dash HLS. There's a huge Dash HLS deployment out there. It is cheap. It is running for years, and then it's working just fine. So whether it's going to be successful or not, that's TBD. And my personal opinion is about 50-50. So with that, I am looking for grad students. I know that there are no candidates in this room probably, but actually I have one PhD student who is older than I am. So if you know anybody who wants to work on these topics, please ask them to get in touch with me. And then this is my sales pitch. 1 hour here in my group is actually 7 years on other research groups. So I'll get them graduated in 1 year or so, if they actually do what I tell them to do. I think that's a great sales pitch. All right, that's it. Zafer and Tuğçe are my students. Here are our email addresses. Obviously, look for a lot of discussions, and AWS for the EC2 support. Thank you very much.
Well, thank you, Ali, for the great talk. And good luck with finding students and some help. Great. So, any questions from the room? I'll go with this side.
The question I have is how much of a moving target is the raw quick standard? Because I understood at Elio World that Quick 2 is not out, and do you find
Quick 2 is out? Quick 2 is not out.
Yeah, I know it's not out. So
okay.
how stable is it? Do you find that there's a lot of interoperabilities between quick implementations because the standard is still changing, or is it still relatively stable?
I mean, the RFC has been out for a year now, so the IETF Quick is the standard, and everybody, including Google, they said that they are compatible with the IETF Quick now. I mean, the major implementations are pretty much, I think, complete at this point. Yes, there will be some differences, there will be some issues, bugs, and things like that, but people are really keen on, fixing them. So it should be pretty reliable at this point.
Thank you. While I pass the mic, can you go back to the slide with email, please? So
which one?
The last slide with the email addresses, so people can take a picture.
Actually, it's up to those guys.
Cool. Thank you.
Okay.
Yeah.
Hi, I'm curious about your delaying non-iframes. Like, isn't there a point where if you have an iframe, everything that's dependent on it, like if you get a new iframe, everything that was dependent on the old iframe, you can throw away?
Well, first of all, I'm not really on purpose delaying anything. I'm just prioritizing some other things so that they naturally get delayed. So there's a difference, right? So I mean, I have so much bandwidth that I can use to send my data. So I am cherry picking what I need to send to the other side.
Yeah, but my point is that if a new iframe overtakes packets that are dependent on the previous one, they're no use to anybody.
Well, the new iframe is going to be like a instantaneous decoder refresh, so it's going to be a new iframe.
Right,
Unless you are
so-
using
so the-
OpenGOPS, it's going to be a clean starting point.
We'll talk about this later. I think there's a big optimization you can do here.
I'm sure there is, yeah. Yeah.
We can do a panel later.
Yes, sir.
A couple of questions. First, regards to Quick, you said there are benefits of Quick over UDP. It is more reliable, right? Does it have any solutions for audio-video synchronization? Does it make it better?
No, that's something you need to do in the application layer.
the
I mean,
application.
quick. The streams are independent from each other, transmission. I mean, so if you put audio in one stream and video in another stream, which we intend to do actually, so we deliver audio even in the case we cannot deliver video, that's something that needs to be handled in the application layer.
Okay, got it. And the other question is around your metric for success is latency. You're basically looking at, okay,
Latency and on-time decoding success rate.
but
Yeah.
then how is quality affected by using Quick and using your methodology?
Well, at 50% on-time decoding success rate, it's going to look like crap. I mean, I was just trying to make a point there, with with prioritization, we improved the success rate from 25% to 50%. But again, they really both look crap, right? I mean, it's not really the main point. I guess the main point over there was, if I can go back to this slide. I really wanted to show this. If you are really very low latency, if you are running at very low latency budget, right? So you require literally 1 second from camera to the display. Frame type prioritization. Even this simple prioritization is going to give you some significant improvement, right? But if you are relaxed, like 5 seconds, 10 second latency, who cares? I mean, the prioritization is not going to really give you much improvement. So Dash HLS is going to be your best bet in that case.
Well, thank you very much. Thank you to the room. And there's a coffee break coming up. We have about
right.
10
Perfect.
minutes-ish. See you back here at the quarter hour with Sandro.
All right, thank you.
Thank you so much, Ellie.